Okay, thank you very much. So it's nice to be here again. I enjoy a lot to be in your workshop. So this time I'm going to talk about service robot, but about home furniture detection and localization. This is the work of two of my students on PhD. So for me, obviously, are very interested in these approaches. But, well, the contents of this talk will be, I'm beginning with an introduction. Then I'm going to talk about the related work. Then I'm going to present the proposed approach. This is the approach proposed by my students. And then, well, the proposed approach for feature extraction and model generation, where we have based all the work on this model generation. And then, how we can recognize furniture and localize on a home environment. Finally, some results, and conclusion and future work. So, service robots. Nowadays, we have service robots in many, many places. We have service robots on museums, offices, airports and train stations, and hotels. But we don't have, until now, service robots in our homes. So, what need to do to have these robots in our homes? Well, you can tell me, yes, there is a robot in our homes. The clean vacuum, but we, as Carlos Sauez told this morning, and Jose also, we think in robots in our homes in this way. Robots to help in many, many tasks, cooking, cleaning, and doing some services in these complex environments. So, what's the problem to have these robots in these environments? Well, there are many, many problems. Until now, we are able to do maps, to path planning, to avoid obstacles, to do many, many, many things with robots. But until now, the robot doesn't understand the sense and the useful or the usefulness of every object in a scene, and then the relation between them. There are many, many, these relations are many, many important to understand what to use, what is useful, for example, a cup or a dish or something else. And if I'm looking for something, where I need to look. So the motivation is introduce these service robots really in our homes. And we need to recognize objects in the environment. But not only recognize these objects, we need to recognize these objects and find the relations between the environment and the objects, and between objects. It's very important in order to help humans. If we don't pass this threshold, this technological threshold, the robots don't be accepted by the humans. If I need to do the RGB cup that is posed at XYZ position with theta radians on the shelf posted by these kind of things, the robot doesn't understand. So we need to give instruction to the robot in order, as we do with humans. So we need that the robot understands the scene, and obviously to communicate with them with this same structure as we use with humans. So we begin with, there are many, many works detecting objects. Many, many works detecting small objects, objects on a table, objects on a scene. But we are beginning with features, with furnitures in our homes. Which kind of furnitures? We decided to begin with furnitures that move in our home, as chairs, tables, the bed, the chest drawer, the couch, and something like that. Because why? Because we are able, as I told you, to do maps. Commonly we do maps as grids, occupation grids, sorry, and where each point of this grid has how to say that, is independent of the point on the nearby. So we compute the possibility of each cell to be occupied or not in function of what the robot see with this laser, with this Kinet or something else. But the points, for example, the chair, are not isolated. They are structured. So if we don't see a point, we didn't see the same structure of the points related with this object. So we are considering as objects that move together. So with that, we are beginning to understand the relation between these points on the map and the rotation, and then to understand the relation between different objects on the scene. So once do it that, we can find the uses and usefulness of this object, and then finally construct what we need to do is a cognitive map. So on a cognitive map, we can do tasks robustly. Well, there are works obviously on these tasks. The first works are from 2004. On these works, there is a cloud of points, and this group segment the planes, the horizontal planes, on two different sizes, two different distance to the floor. So they say that maybe there is a chair or a desk. However, it's not enough to compute this kind of resolution. There are many furnitures that have the same size. So only to segment by size is not correct. But they are the beginning of these works. Recent works, for example, in 2015, use CAD models. These CAD models are computed against the point cloud, find it on a scene, and then they find the depth, they correlate the points, and they find from a very big database of 3D CAD models of furnitures, which of the furnitures belongs to what the robot sees. The results are impressive. They use relations between, for example, they find planes. It's a horizontal plane, it's a vertical plane, then it's a chair, then can be a shelf plane, a chair seat plane, and they begin to make these relations. However, they use 9 seconds to analyze one single image. It's very hard, this kind of analysis, for a robot that need to evolve continuously on the environment. And for a scene, a completed scene, 145 seconds. So we need that the robot do task robustly. We can wait 9 seconds every time each take a point cloud in order to detect this kind of objects. There are other approaches, for example, to categorize some planes in function of their normals. And one of the more interesting for us was the project from Dust, because they propose a feature vector composed by 4 elements, in this case F1, 2, 3, and 4, taken from 2 points from the point cloud of as the same object. The points are the distance between the points, the angles between this vector, the vector union these points, and something else. Well, they made a hash table, and they find which point, on a scene, which of these points belongs to an object. The results are very impressive, very impressive. They can they can compute many poses of different objects as with occlusions, but the objects are very different. If the objects are very similar, the feature vectors are very similar. And in the case of furniture, this is the case. There are a work called SLAM++, and they use the same feature vectors in order to localize this kind of chairs and tables. And then the results are impressive. I don't know if I can turn the video here. So with a KiNet, they can recover and find, as with these feature vectors in real time, the furniture, the piece of furniture on this environment. They begin to pass the objects there. However, we have tried this furniture detection with these features. And for us, for example, we are interested in the bed, in a chest of drawers, in 3 kinds of tables, a dining table, a small table, a bedroom table, and all the objects have the same features. It was very difficult to this model to find the match between objects and the scene, because the hash tables are very similar. And another inconvenience of this approach is that the error on this approach in localization is 15 degrees. 15 degrees for us, for robots navigation, are very high. So we need to improve this kind of detection and localization, and we have think about how to solve the problem. But the problem, we need to solve the problem in real time, and we need to solve the problem accuracy, with more accuracy. So we begin to analyze this scene, and we have found that, well, it's not, it's obvious, of course, that for furniture, one of the more important characteristics are the planes. And we have seen on this scene that the horizontal planes are very important. We used to pose objects there, or ourselves to go to bed, to sit, or something else. So the planes, the horizontal planes, are very important on these environments. This is another example. For example, here are colored these planes. So why not to think different? I didn't show another works, but commonly we use ransack methods to find planes on environments. Ransack methods usually take about 1 second, in the best of the cases, to find the 10, 15 planes on the environment, but depends of the complexity of this scene. Then why not to use the information beginning from the robots? We use 2 kinds of robots, Max at the laboratory, LAS from CNRS, in Toulouse, and Huberto at the University of Veracruzana in Jalapa. So why not use the information of these robots and reduce the complexity of the scene? So we begin thinking about transformation, because we have the transformation between all reference frames. We use ROS for all those robots. So we have the transformation between all reference frames. Well, we have pantil units. So all time we have all the transformation between all reference frames. So we can convert all point clouds in a reference frame fixed to the point location of the floor where is located the robot. So we transform all the point clouds. We made a histogram of height for these points, and we found this. What is this? This is the bet. We found that really, as we have think, there is a feature. This is the feature. This all the points that belongs to the same size. So when we do the histograms, we found exactly the feature as we need. There are obviously points below and upside, but we are interested on this kind of features. We have made for the coach, and we have made for the chest of drawers. This is the average. The blue curve is the average, because we made different points of view of the same object at 45 degrees, I think, and we have rotated the object, and we take many scenes. We have the average, and we find that mostly of the time we have see this display. So, okay, why not to model the furniture as distributions of points in a reference frame that is the floor? So we have decided to do that. We have do with all those furniture pieces, and then we have made the same for colors in the HA's space. So we have the same. There are some peaks of these distributions, and finally we have made this for normals. Then for normals, they are very different, the distributions of normals for each piece of furniture. And what is more important here is that these histograms are computed on constant time. So we don't need to do some random searching or another kind of thing to find this kind of features on these distributions. So the problem here is, okay, we have distributions, well, we have modeled each piece of furniture with these distributions. So how we can find this distribution on a scene? On a scene, we have that, sorry. So it's a mix of the distributions. So how can extract the distribution that we know that belongs to each piece of furniture to this on this scene? So we are at the beginning interested only on the peaks. So we segment the peaks. Once we segment the peaks, we find, well, this is another scene, sorry. We segment the peaks of this distribution. We clusterize the point clouds of this scene. Then we analyze the distribution of colors and the distribution of normals, and with that we make the detection of each piece of furniture. Then later we use the CAD model, we can use the CAD model to localize with each point cloud, segmented point cloud, each piece. So more or less the model is this way. We have a scene, we have filtered, we have the piece of furniture, we extract the characteristics on the height, the HA's space, and the normal distributions, and then on a scene we try to find the segmentation of these characteristics. So here I seen here in white the planes detected and some results. For example, here's the bed. We can segment the points belong to the flat, well, not exactly flat, but this horizontal plane. And we pose this plane on a map. Then the chest of drawers, we segment this. And finally, we can locate many, many pieces of furniture on this map only with this kind of distributions finding on each point cloud. Here, I have a video. I'm sorry they are not synchronized, but this is a typical navigation of a robot. Each time it segments each piece of furniture to finally locate it on a map. So we don't do plane detection explicitly by computing the point cloud and then the normals and then the stand, or by region growing or ransack or something like that. We use distributions. We segment distribution. We are using this distribution to detect those planes. And those planes have different characteristics. For example, we use the bed, that the distribution of the points on the bed, the Gaussian distribution, are bigger than, for example, the points on the table. So, adjusting a curve to those distributions, we can recognize to which of these distributions, to which model each peak corresponds. Okay. So, reduces computation. Recognition and localization now is done at 400 milliseconds. The errors we have are 5 centimeters and 5 centimeters. Why? Because our localization grid is 5 centimeters cell. Each cell is 5 centimeters by 5 centimeters, 5 centimeters square. And 2 degrees are the errors that we have found in relation with this localization. So it's very, very, very efficient, and it's very easy to compute those features. Future work. Well, now I'm going to return, maybe I have, this is interesting. This is the chest of drawers. This is the main horizontal plane, the top horizontal plane. But we are only characterizing the peak. If we see, there is also a feature here. There is a distribution of points here. At this moment, we don't characterize the curve completely. We are only characterizing the peaks of this distribution. So maybe a curve fitting on those distributions will be better to find those pieces of furniture on the environment. So at this moment, we use a localization to raise the walls. Okay, yes, maybe it's tricky, but we think that you can move, for example, from one house to another, and you can take your robot with you. Then it makes the map of all components that are fixed to the environment, and then you put all your furniture pieces. Or maybe you have the CAD model of your home. Then we can localize the robot and use those. But, well, also the future work are improve learning and test on different environments. This was published on this conference, and we have now some new results that I'm going to present maybe. Yes. Now we are able to have all those planes, so we use the same principle to project all the points on a 2D distribution over the floor, and then we can segment all vertical planes on the same way without using ransack or plane estimation or something like that. So constant time is very, very important. These are order. So we can erase now walls easily. Or localize also these walls. It's another. So, well, we're using ROS. We develop many packages for ROS, and we put those packages at GitHub UB Robotics Lab. So if you use these packages, please tell us to know what do you think about it. And obviously, if we can construct a community around ROS to have more packages, will be very, very interesting for us. So all those packages are available on this GitHub, and you can use it for your own robots. So if you have questions, thank you.